Hello, and this is IGB381 Game Engine Technology, Lecture 5 on Advanced Lighting. So, we've covered some basic territory in the unit. We've moved ourselves through setting up shaders, enhancing the rendering technology that's available to you. We've gone through simple lighting models, taught you a bit about CG, and then gone on to texturing and anti-aliasing, which is sort of basic concepts. Now we start to move further and deeper into how to simulate lighting in computer graphics. So as I presaged in the first lecture, we have to touch on physics in order to actually cover the content. So this is not a unit that is light on. Some people have been commenting about the theory in the unit. I'm afraid if you wish to understand how a game engine works, you have to dig deep into the theory, and that theory is mathematics. The mathematics is used to simulate the physics of a lit environment in a game to make it visible. And indeed, you have to simulate the physics for object interactions, you have to simulate the physics for a number of other elements, you have to do mathematics for the artificial intelligence, as you'll learn with David Conroy in IGB383. All of these things require a theoretical basis to be laid down, and then you do the implementation. So, suffice to say, you want to work with game engines, you need to understand the theory. And another thing, theory is a general model. If I just taught you Unity and nothing else, you don't have a general view on how to do game engines. If I give you the maths, you can take the maths and build your own game engine or use another game engine and understand more deeply the concepts they present. Texturing is in the UDK and other engines. Phong lighting is a part of most game engines. All these things are there, so understand your need to absorb the mathematics to get deeper into a game engine as a software engineer. This is why the unit is set up this way. So let's move into the lecture proper. So I'm going to give you a bit of a background on radiometry, photometry, colorimetry, where we start to get deeply into how you specify colors for humans. Because we're not standard sort of measurement devices, and RGB starts to fall down when you're talking with humans. And then I go into some advanced lighting models, in particular, just to comment on BRDFs. And then at the end, I'm going to just do some bits and pieces just to tidy up the pipeline so that you understand the viewport mechanism that you're using in Unity and its place in the complete graphics pipeline of transforms. So without further ado, again, why all the theory? Well, all of this provides a basis for the global illumination, don't say that too fast, and via radiosity and its similar methods in other engines. These things can be now delivered in real time. In fact, interestingly enough, NVIDIA are now saying we can do ray tracing in real time. Now this is a fundamental shift. This means that the underlying technology can now capture light effectively and implement it for you as a game developer to build into your games. So Unity uses, since Unity 5, the Geometrics Radiosity Toolkit. You'll see there's just a video where you can see how they've used global illumination in Unity. So when you're looking at the really top-end Unity demos and the movies that are being generated, the Geometrics technology is being used in that place. And that means if you want to use it, you need to understand a little bit of the physics that's driving that system. So light is treated very differently to the simplistic models that we've done with our direct lighting that I've been teaching you. So I'm going to take you to global illumination soon, where it gets all a bit scarier. But in principle, all it means is you just account for everything in a scene as being a light source. That's it. So to do that, we have to have a physics background in order to at least sort of grasp some basic concepts to move into utilizing these techniques effectively. So, as I said before, most older fixed function pipelines, this is an example of a game from years ago, which now continues on unabated on the PlayStation. And you can see that the old version, lots of flat surfaces, not particularly high quality graphics. But you have and the lighting is lighting, but it's not that real. It's just Phong lighting. It's the stuff that I've taught you so far. That's what computer graphics was for many years, as I've said, in real time. Now with programmable shaders and much more realistic capabilities, such as global illumination by spherical harmonics, baked on lighting, all sorts of things, you get Liquid Snake looking much more realistic in this scene. The thing is, the old versions gave you a vision of everything made out of plastic. Phong lighting models plastic nicely. Everything looked plastic in old real-time systems. That's not going to cut it in the modern arena. And so therefore, we need to advance beyond just this Guru shading, Phong lighting, and texture mapping that we've had since the 70s. I mean, Jim Blinn came up with it for the Voyager images in 1977, I believe. So those gross approximations need to be refined to give you a better looking graphics for the present. So we can now start to use the GPU hardware to model the photon's interactions with the surface of an object to give a physically based appearance that is photorealistic. So that means you can start to have other things other than plastics. And this is important because that starts to make the scene believable, the levels of immersion increase, and you are involved more in the scene. It also brings out some interesting fun that you can do with the lighting as far as, even the gameplay is influenced by this. You have much more control over the lighting. And finally, you then have control over the character of the lighting. And you can create lots of stylistic effects, which I come to cell shading and so forth, where we start to play around with how you can deal with the color. So we have to dig a bit deeper into physics to get an understanding of what's going on in the scene, so that when it comes to using these systems, you start to understand what's going on and why these scenes are much more realistic. And the truth is, we probably just go about in life wandering around thinking, I see things. But there's a reason you see things the way they are, and it's based upon the laws of physics. We have to model those laws of physics in the game. So, put short, those K values, Ks, Kd, and Ka, for specular, diffuse, and ambient parameters that I talked about in Lecture 3, they're just set to arbitrary values of between 0 and 1. So you can control them, you can play with them. I gave you that Phong and Guru demo. You can play with those public parameters and just make the thing look different, but it keeps looking like plastic because it's a very simple approximation of the light incident across the surface and its reflection. So, we can darken the scene, we can play around with diffuse parameters, we can change the lighting colors, make them blue or red or green or mixtured objects. We can change their shininess, more plastic or look like a dull plastic. And so that means with that, we can sort of got a very limited set of materials we can model. Diffuse matte objects, so if they're painted with matte paint. Shiny plastic objects, because the specular light tends to be the color of the light. Metal objects, the specular color tends to be the object's color. But again, it's not very realistic with the techniques I've so far shown you. It's very simplistic. It's a simple little function with a dot product, L dot N, that I keep talking about. And we need to be more sophisticated with that. So we need to understand how light works and how it is measured. Once you've measured it, you can then build functions to model it. And the models of photons as particles work for most situations. So we're not going to get into quantum mechanics. We're just going to treat it that the light sources, such as the window glaring behind me in this video, is just a sequence or a series of trillions of photons emerging from the sun, bouncing around on the planet, and some coming in the window and striking the CCD on the camera in front of you. And that's what you see. And that's enough for us. We're not going to do wavelength properties like polarization, phosphorescence, and fluorescence. They can be cheaply imitated. Just look at your standard fantasy games. They've got lots of glowing things. It's all good. And that's a nice approximation in those environments. But we're not going to model them at any depth. But we're going to just treat the fact that a light source emits a slew of photons into the scene. They bounce around, come into the camera, and you need to be able to model that effectively. So what are photons? I'm glad you asked. This keeps me up at night, worrying, quite frankly. What is a photon? Keeps a lot of physicists up at night worrying. But the idea is that the photons have a particle-wave duality. I'm going to stop there, go into a physics degree, and you can dig right into what is going on inside a photon. And so a photon has a frequency associated with it, like a wave. Photons are emitted from a light source and absorbed by objects depending on the wavelength. So I've talked about this. We've got those 4 things, and one of them is about absorption. So the 4 ideas in light. So there's reflectance, transmission, scattering, and the 4th one, because my finger won't come out, is absorption. And absorption is the issue you face if you're trying to model color. Because the absorption that happens in the physics, as humans, we perceive as color in our consciousness. If you want to talk about consciousness, go do a philosophy degree. But staying here, we'll just say, right, you're a conscious being, you're looking with your cameras at an object, and it's a certain color. And the reason it's a certain color, that color experience, subjectively, that you have, is correlated with the wavelength of the light or the photons that come at your eye. Thus, red objects, and this is because of the absorption factors, red objects absorb all photons except the red ones. The red ones bounce out and hit your eye. So you just think it's red. And the problem, though, is that it's not as simple as an RGB color model. So the perception of color is not based on a single wavelength. It's actually a distribution, a mixture of wavelengths. And we as humans interpret that spectral distribution of wavelengths and see it as colors. And we're able to communicate, talk to each other about yellow objects, red objects, and blue objects, because our subjective experience seems to be consistent with each other. There are differences, and people have a certain difference in the way they perceive color, but by and large, we're pretty clear with each other what we have as color. This is not accounting for color blindness. That's where the senses have something different about them. That means that the person is not able to perceive reds and blues or blues and yellows. And this is due to the way the human visual system stores color. I won't go into that. So most of the time you've been playing around with colors, either in Unity or playing around with Photoshop or Maya. The colors are generally RGB values. That's how you've seen it. You mix it up using RGB. But RGB is a poor approximation. It's a really poor approximation. And it's also difficult to use. I'll get to that later, where some other color spaces are much better for humans to use. But RGB is great for driving the guns or the LCD systems inside your displays, and that's why it's used. It's a hardware interface. It's not a human interface. So if we want to understand light, we need to understand it from the physics, but then I'm going to take you through the process of translating that into an accessible form for humans and an accessible form for comparing different hardware. By the way, as you can see here, the light waves occur at different wavelengths, and the frequency, so it's the number of waves per unit time, hertz is waves per second, and you notice that the wavelengths change. So up the top here we have the red. It's a longer wavelength than the short wavelength purple or blue. And in fact, purple for humans is a combination of red and blue. We don't see into the violets. with a primary color. I'll get to that in a minute. So primary colors mixtures of them enable this complete visible spectrum, but we can only detect things we can only model them as reds and blues and greens and mix them together to get our colors. But you can see here the progression. As the wavelengths get shorter, they have more energy, and you go from red to the violets. Note, you perceive outside the visual spectrum light as heat. When it goes red, infrared is what you feel when you're near a hot object. And ultraviolet energy starts to get into the really dangerous shit that atom bombs throw at you and kill you with. The sort of slightly dangerous stuff is UVA and UVB, which is just out of visible spectrum for humans, but it burns your skin and you get skin cancers. Like the one I had removed here one time that could have killed me. So these sort of things, you live bathed in radiation. Most of it is harmless, some of it is nasty, and your body has methods for dealing with it. We'll deal with the non-nasty stuff. So some definitions to set the scene. So radiometry deals with the measurement of radiation throughout the electromagnetic spectrum. So typical, it's around optical radiation in the frequency between, say, 3 by 10 to the 11 and 3 by 10 to the power of 16 hertz. So these photons wiggle at a very high speed. And that means their wavelengths are, say, something like 1,000 to 0.01 micrometers. 1,000th of a meter wavelength. 1 millionth. So this includes, as I said, infrared heat, visible light, and then onto the high energy spectrum, such as ultraviolet regions of the spectrum. So we'll just worry about the visible bit, because that's what we've got to deal with in our scenes. There. So that's radiometry, covers all the spectra. That's what you do if you do physics. You do high energy physics, infrared spectroscopy that is used in astronomy. By the way, a small bit of trivia. Brian May, the lead guitarist out of Queen, he's a specialist in infrared spectroscopy as applied to astronomy. And he got his PhD in that somewhere in the 90s. Smart man. He also made his own guitar. But back to this. Photometry is the same radiometry weighted by the sensitivity of the eye. The eye does not perceive every piece of radiation. It's got a small band. And that band we've evolved to be sensitive to because it enables us to make decisions about whether it's a good food source, whether it's something worth mating with, or whether it's a nasty thing that's trying to kill us. And so photometry deals with the visible spectrum from 380 nanometers to 780 nanometers. So these are really small wavelengths. And so things such as blue, we'll call it blue because it's actually spread, is around 450 nanometers. Green is around 540, and red is around 650 nanometers. So when you're seeing those colors, remember, those wavelengths that are not being absorbed get reflected by the object and you perceive it as the color, and the wavelengths match sort of to those hues. And sort of is a really slippery concept. So photometry does not deal with the perception of wavelengths though, just this perceived strength. E.g., is the green brighter than red or blue? And the reason for this is color is a human phenomenon. It occurs in your head. It's related to the wavelength, but your perception of color is entirely up to you as a subjective primate. And that's it. And we have some other animals, primates have it, and a few other animals have color perception because we can do experiments with them and tell that they know colors. But other animals have no color perception. Often predators don't have color perception. They don't need it. They just eat anything that moves. So, but that's a generalization. There'll be animals that can eat other animals and perceive color. But just saying, there is this division, it seems, in animals and their color perception. I won't go into that. Do a biology degree. There's so much to learn. So the photometry that we've done is converted to photometric units via the photometric curve created by the CIE. I don't know French, ich spreche Deutsch, nicht Französisch. So it's the Commission Internationale des Éclairages, and they are an organization that during the 19th century decided they would try and quantify color because of industrialization. You need to understand color. You're going to make paints, lights. You're going to make things look fancy. You're going to dye fabrics. You need to understand color. It's an industrial thing. So here is the photometry curve. And this is just from experiments. They performed experiments. They knew the wavelength of the light coming out of their light sources, and they detected, they got people to record their subjective lightness of these lights or these sources using various experiments. I won't go into it, but you get this curve. So remember those wavelengths I mentioned. So at the visible end of the lower end of the spectrum, we've got the reds down here, 450 nanometers wavelength. Higher up here, 650, you're heading towards the blues, the purples, and out into invisible high energy radiation. In the middle is the green. Note, why is it that we are centered on green? Is it an accident? I think not. Take a look outside into nature, and nature is strongly green because the planet is covered with plants. So you as a human need to understand different hues of green so that you can determine different styles of plants, potentially to eat, also to be able to see a predator against that color background. They'll be camouflage, but you might be able to pick different hues. Humans are capable of about 16 million different colors. We're quite sensitive to color. And so we're centered on green because we've evolved that way. It makes sense. We are tuned to the environment that surrounds us. And by the way, men and women are slightly different in their responses. This may lead to arguments about color between couples. But there is a recorded difference in how men and women see color, and I believe that women are more towards a lighter shade of green as their central response, and men are towards a darker shade of green. There may be nothing to intuit from that. There's just a difference, and we perceive color slightly differently. And the units in the conversion curve are the difference between photometry and radiometry. So radiometry, that deals with radiation in all sorts of spectra. Photometry is about humans and the visible spectrum, and it's based upon this curve. So that means any radiation that comes through, we're most sensitive if the wavelengths are in this band. Everything else, we don't have any sensitivity. The curve is very low. We don't respond to it. We can't see it. It might fry our skin, but we won't see it. So radiant energy from a light source Q is in joules. Remember from your science experiments at school? As a measure of energy. So each photon, tiny little packet, tiny little packet, nanometers in wavelength, they're not big, pouring out of all the light sources around, has a radiant energy equal to Planck's constant, 6.62620 by 10 to the power of negative 34. This is a tiny number, but each photon has that value. And it has, energy is in joules, and it has that number, joules seconds, times the speed of light, 2.998 by 10 to the power of 8, a pretty freaking huge number, meters per second. And then you divide by the photon wavelength to finally get its radiant energy. So that radiant flux, or radiant power P, is the number of joules per second, the change in light source Q, the change in Q over time, and that is known as watt. As R watt, sorry. That is known as watt, pun intended. So that is therefore why when you buy a light bulb, it has a wattage associated. And what it's simply saying is how many joules per second are emitted by the light bulb, and that's related to the photons coming out, which is a particular wavelength. Typically, you buy white light bulbs. But now with LEDs, people are buying colored light bulbs, so things are changing. But they still have a wattage. It's how many of those photons are coming out per second and hitting your eye gives that brightness. So that's all you really need to know here. It's a simple equation. I go through it in the tutorial just to open your eyes up to the fact that watts means something. It means lots of photons hitting you and bouncing around the room and hitting your eye. And that's why you see things. There's no magic. It's all science. So we need to measure how those photons arrive. So we know that there's a source of light in the scene and it's blasting light out. So we use a term called flux in physics to measure this. And the radiant flux density is the radiant flux per unit area on a surface. So let's get a surface. My keyboard, for example, got a nice flat surface here. So that's just, it's an area, all right? And its perceived brightness by you can be measured by that flux on its surface. So it's dark because it's dyed black. But if I get my Macintosh keyboard, because, you know, got to think safe, it's white. So its flux is higher, so it's brighter. And also it covers all wavelengths, so it sort of has a white tone, whereas the other one is absorbing all wavelengths, so it looks black. And so we want to know the amount of light hitting that surface. Why? It determines its color and it determines its brightness. And that's important if you want to light a scene. So that means this could be a polygon, a triangle, or a set of triangles, or a mesh hanging in space with a lit scene or with a light on in the room. And we want to know how much energy is reflecting, how much energy is coming into this piece of polygon. Because that enables us to model the light in the scene and to produce a visible image. That flux can be measured anywhere. It's passing through space. So, you know, I could measure it here, I could measure it here, I could measure it here, I could measure it up behind my head. And I've just hit the keyboard. Take it back. Very good. So that means it travels through space. So the flux density, this energy, is the rate of photons flowing through it each second divided by the area. So here's our scene, Apple, rubber ducky aeroplane. And the flux is the amount of light hitting every second going through an area towards the object in question. Now that doesn't necessarily mean how bright it is, it's just that there between it and the light source, energy is floating towards it. That's one point, that's one component. You have to calculate how much light is coming towards you, but the amount that's reflected determines how light the object is. So if the light source is far enough away, it's constant. It's just a value and there's no real change. It is fluxing, but it's just you have this area, you have amount of light going through it in space, and it's related to how far away you are from the light source. So remember, as you get further and further away, your radius increases, so the amount of energy subtended over the area increases. If this didn't happen, you turn a light bulb on and the room would just end up bright white after a very short period of time. Because the density of photons disintegrates, fades out over the area of the distance, you have that sense of, you know, somebody takes a light bulb and walks away, the whole earth isn't lit by the light bulb. The density of photons gets less and less the further and further away from the light source you go. And so the person walks away with their torch or their light and it becomes dark for you. This is how it works. So for an infinitely small area, The flux is going to be d phi dA, where phi is the radiant flux P on the surface and A is the area. So if the flux is uniform from long enough distance, we just divide the flux P divided by A. So irradiance E is when flux arrives at a surface. So remember I said the appearance of the bottom of this keyboard is going to be a component of that E coming towards the surface, and then the radiant excitance, M, also known as radiosity. Remember that word, radiosity. It's the bit that floats back towards your eye. So I could have a lot of bright light on this, but this is a dark object. It'll reflect only a certain amount into your eye. And in fact, you're only getting a chunk of what it's hitting its surface. And you're saying, why are we doing this? The reason is this is how light works in Unity. They calculate this flux and they approximate it as a radiosity term. And you need to know that when you're playing around and using the light probes and the radiosity geomerics engine that is inside of Unity. So this theory is implemented in Unity. So this is where we get to the cos theta term that I've been rabbiting on about. So L can be independent of surfaces and just represents the passage of light through a point in space. So the flux is just traveling along at the speed of light in air, changes depending upon the media it's going through. Again, do a physics degree. But it's rocketing towards this surface and then bounces off it into your eye. So the radiance is defined with respect to the power per unit solid angle per unit projected area. Put simply, as you can see in the diagram here, we've got this light heading towards the surface through a fixed area or through a changing area as it diminishes away from the light source. And depending upon the angle as it hits the surface, so here's the surface and here's the area of light coming towards it, the lower the angle, the greater the size of the area projected onto the surface. So think about it. If I face the light source here, it's a coffee cup, use your imagination. Here's our polygon. If I face the light source, it's bright. But as I rotate the polygon away from the light source, it becomes darker. The reason being, the projected area of this light source onto the surface gets bigger. If the area is bigger, but the flux is constant through space, it falls off. And it's related to that cos theta term. And that's the dot product you see all the time in lighting systems. So this means that this gives us a nice mathematical foundation for saying, right, there's an object in space, it's emitting light, it travels through space and it hits the object, and if the object is some distance away and is at a certain angle, then you get a certain amount of light bouncing off. And that's the basis for radiosity and global illumination in high quality game engines, such as Unity and UDK. Move on to the next slide. Stop highlighting things, Ross. So, put simply, we have a number of variables. We've got 3 for a location in space and 2 for direction, light coming in and light bouncing out. What does that remind you of? It reminds you of an environment map. Remember, on the surface, when you made those metallic objects that I showed you in the last tutorial, you had a point, there was a normal, there's the I vector and the reflectance vector with the environment map. That reflection, you could do it in the other way. The environment map is taking color and putting it onto the surface and then bouncing into your eye via that vector. So if we want to generalize light in a scene, imagine that at every point on the surface of an object, you generate a new environment map. All right, so you generate that cube that I showed you last week. So you end up with a separate environment map for each point on the surface of the object. Why? Well, think about it. When you're on top here, the light bouncing from below is not going to matter because it comes through the sphere. And if it's solid, it won't get to that surface. The same here. If you're on the bottom of the sphere, the light from coming from above will start to be occluded by the sphere and won't emerge here. So you need, if you're going to get accurate light that mimics reality that you see around you, because this is what happens. If you have a sphere in reality, the light that's hitting it tends to come from the top, not from below. So you need, if you're going to model it, you need to create an environment map to suit that location. So that means the radiance distribution in a scene is all the set of environment maps for every point on the surface of an object. That's what you need to model. Now, that's a brute force method, and in the end, it's somewhat what ray tracing does. Radiosity has some solutions for doing this far more quickly, and that's how we can have real-time radiosity in modern systems. But that's just how you think about it. So when you look at the surface of an object, like this coffee cup, every point you would generate a new environment map to model the light hitting its surface. So as you can see here, the bottom part is a bit darker. Why? Because actually most of the light is coming from the back here. And you get this sort of, this side's darker because the environment map, the sampling of light around it, it's not as much light. There's more light coming from here. And that's how it looks. So if we're going to make things look real in a computer graphics engine or a game engine, you need to do the same thing. And that's why you find some of your Unity games look very realistic. Okay, now, moving on, that's the physics basis for light. The broad brush strokes, just so you understand the basic principles about light traveling through space and reflecting off. Here, we're going to talk about colorimetry. So this is the perception of color as light bounce off a surface. So as mentioned, we perceive light in the visible band 380 to 780 nanometers. Alrighty? So we're dealing with a narrow band. That's what creates our graphic scenes. So the light from a given direction has photons with a distribution of wavelengths called a spectrum. And here's an example here. And funnily enough, I don't know why, they chose a ripe brown banana. I was fascinated by what they choose for scientific experiments. But anyway, let's keep moving. So here's, you can see at the bottom there, the wavelengths in question. So that's the visible light spectrum, you know, from the large wavelengths up here, heading to reds, down to the blues down here, and the greens in the middle. And you look at that curve and you can see, well, there's a fair bit of red because it's brown. Okay, let's just make sense of it in a descriptive form. This is brown. You know the color of a ripe brown banana. It's a brown color. Well, interestingly enough, if you were to paint that, just imagine you have a paint source, you'd probably add a lot of red and a fair bit of green. And you can see the spectra has a lot of that light reflecting off it. This stuff all blue. Think about it. Brown, or the brown of that banana, is a sort of reddish color. And you note it's not completely bright. It's not up to the highest value. It's sort of, at certain points, it's sitting about 60%. So you think about it, brown is a greeny mixture of green and red, so orange, dulled down. That's brown. My last name, by the way. So in this circumstance here, you can start to understand the spectra. Here, the colors, you've got a lot of reds and a lot of green, and then it just drops off because there's no blue in brown. Well, sorry, there's very little blue in brown. But notice as well, there's no hard and fast sort of shape to the curve. It's a weird looking thing. You create it by measuring, and then you could probably fit a curve to that if you're a mathematician. But understanding for those who are not mathematicians, this is just what a device tells you. It says that you get this much blue, you get this much green, and you get this much red. And it's different for each of the wavelengths. So see how, if I was to draw a line from the bottom to the top for a particular wavelength, say 700, I hit there. That's how much 700 nanometer wavelength I get. This is how much 550 nanometer wavelength I get. And I get stuff all 450 nanometer wavelength, which is the blues. So when we look in the world, that's how we see color. Our brain is receiving a signal via the eye containing these spectra. The world is not an RGB gun in a monitor. The world has photons bouncing off according to the radiosity calculations I showed before, depending on the area, and those photons hitting you have this spectra. That's how you see color, but you give it a name. That's how humans do things. We semantically label things. This is one of the reasons why we think humans have a lot of capability with color. We're quite sensitive to color. We're very good at understanding shades. So it's about 10 million different colors can be just understood by a human. We may not have a name for all of them. All right? But we're able to distinguish the different shades. We can see them and say, oh, that one's a brighter blue than this one. And you might look. And companies like Pantone, and those of you who do art, you understand this, generate these color swatches. You go to a hardware store and you want to buy paint. You've got all those shades, you know, those little... In fact, I'll just go and get something. This is what happens when you're at home. You can just rifle through stuff, right? I'm not sure how because I can't see my camera view from here. You should see some fabric colors for some blinds. Yes, I went shopping for some blinds with my partner. And you see these colors, they've all got names on them. They're little color swatches that have been given a label because they appear attractive to people and they harmonize with other colors. That's the whole subjective experience. The simple fact is all those colors have different spectra that I'm highlighting there. So if I looked, and they give them names: wholemeal, spice, bark, jasper, storm, state, peppercorn. All those things are then labeled with names, and that's how humans deal with color. But the funny thing is, its physical basis is a spectrum. And this is because humans convert that spectra, we perceive it as a subjective experience, as a conscious being, and then we give it a name. And that's why, in philosophy, they often talk about the color red. And they use a word called qualia, which is Q-U-A-L-I-A. The subjective experience of red. Where does that come from? Because the reality is, it's a spectral distribution. So the next time you're arguing about colors with your friends, you can start to get quite philosophical on their buttocks by saying the distribution doesn't match to the word. The word is red. What do we mean by red? Well, it's this distribution, but somebody might come along and say, well, that's red. Oh, no, it isn't. The whole argument about this makes it hard. And this is the point I wish to get across to you, that color is a difficult thing to define because color is a part of our subjective conscious experience of the universe we live in. So that means we need to carefully think about creating some ways of defining color and matching it to perceptual responses so that we can easily compare and make sure that a color that appears on my Mac looks very similar to the color that appears on my Windows box or on my overhead projector. If I was giving you a lecture on this, I would point to the projector and say the colors out of that projector are different to the one on the screen. You know this because sometimes you turn up to give a talk and your video does not look as good as it does on your monitor, because the projector does not show those colors. And that's why we're doing this. It's a part of computer graphics that in some ways is neglected, but I think is actually important because it tells you something about maintaining color constancy. So, human visual system responses. The HVS, the human visual system, has three different types of cone receptors. Okay, each responds to different wavelengths, and the brain receives three different signals for each spectrum. So that means, because they've looked at the hardware, the wetware inside your eye, and that means there's three signals coming through to your brain. These three values can be used to represent any color. All right, that's where the trichromatic system comes from, where you've got RGB. But we don't know what those numbers are intrinsically. We had to do the science to figure it out. So the human visual system sending these signals to your brain, and it's receiving them and dealing with them. But we want to be able to build a function of that that we can use as computer graphics experts to model color effectively. So, those natty people from the CIE, again, Commission Internationale d'Éclairage, the International Color Commission, I think, is the French translation. Read Arbenstein, you'll be able to tell me from your Duolingo exploits. After a set of controlled color matching experiments, they came down to, actually it's the International Commission on Illumination. You might want to read ahead, Ross. They came to the conclusion that there are certain color curves that enable us, with a mixture of these curves, to match any color in existence. So they'd sit people in a room with a sort of set illumination, and they put a test patch of a single wavelength, and then they get another patch, and they get people to twist some knobs to control three different lights until the colors matched. Because everybody's slightly different, they had to figure out how they would match. And so those matching curves that came from that experiment are shown below. So this is the basis for blue, this is the basis for green, and this is the basis for red. But note, red goes negative as a function. It takes away from blue and green in this area. They're just functions. They've come from these experiments. So it seems that people had to make, in order to make these curves work, the red has to be actually subtracted in value from the other curves to make the colors match. So just trust it. It's a curve. That's what the experiments gave us. So those matching curves enable us to create a color that matches humans' perception. So given a single wavelength of light, three color values can be read off the graph, lights set, and the lighting conditions normalized to give an identical perceptual sensation from both patches. This is key. It means you can judge that this color will match this color using a function. So given a spectrum, multiplying by the curves and taking the integral of that multiplication gives the relative amounts to set colored lights to match the perceived color of a spectrum. Now, that may be something that you're not that excited about, but it matters a lot, because those patches that I showed you, you need to have machines that will match those colors to make sure paint, monitors, the computer graphics systems you use, the printers, the projectors, the printouts on cardboard pamphlets, you all have to be able to control the color that appears, and you have to make it match across different devices, which I get to later. So that means that very different spectra can look the same to the viewer, and these matching spectra are called metamers. Probably that's a more abstruse or abstract thing, but just to note that you can have very different spectra when added together, and allowing for the human visual system will look the same on the screen in front of you. Just to make it hard. So, in order to generate color in a consistent space, the CIE proposed three hypothetical non-monochromatic light sources as basis functions. So, you mix these together and you get the appropriate colors you want in a consistent fashion. So there's a Z bar, an X bar, which has two peaks, and a y bar. They're basis functions. Multiply these by a number, add them together, and you will get the spectra that will create a particular color you want to specify. So given a surface reflectance and light source produces a color, which is a color lambda, which is based upon these three basis functions. And that enables you to generate the colors perceptually equally. So what you do then is you have a color. You've measured it using a device, C. What you do is you take that color spectrum and you multiply it by the three basis functions, giving you three values, capital X, capital Y, capital Z. Now, I've used a meter that gives these values. You can buy devices and you point them at a color, they use these fitting curves, and they give you X, Y, Z. They're calibrated. If you go down to the physics department at QUT, you can borrow them. I did when I was doing my PhD to make sure my images were correct. So, and so those X, Y, and Z values are weights that define a color in a particular space. It's sort of RGB, but it's not RGB. It's perceptually aligned with the human visual system. So that's a bit awkward to use. So what they do is they've normalized it so that if you add the three together, they will equal 1. There's a particular reason for this. So these coordinates can be then mapped to another space, a CIE color space. So there's the capital X's. So remember they equal 1. So that means if they normalize them, so they go X is equal to X divided by the sum of them all. Remember they all equal 1. So it's the component to get of that. And you can get Y by saying Y divided by X plus Y plus Z. They add to 1. Z, you can calculate the same, or you just go 1 minus XY. Okay, now why do we do this? Well, that means our color space is normalized to a plane. So here's the Y, X, Z spaces, but if you apply that equation, you end up with a plane that intersects at 1 on all the axes. Intersects at the axes. And any color that fills, say, the cube space of X, Y, Z, so it's 3 dimensions, so it fills the space, are mapped to that plane. So you can see there that this is actually the RGB cube deformed to suit the human visual system. And then a slice is taken through it to get a nice color space that is usable. And you'll see it here. And that plane is then projected onto X and Y because the Z can be calculated by taking X and Y using this equation. So Z is equal to 1 minus whatever X, Y values you use. So it's a trick. That means you only have to deal with color in 2 dimensions, which makes it easier for a human to cope with. And that space there is called the CIE color space. And it looks like this. You may have seen this. Sometimes people have played around with color. You may have seen this shark fin. We call it the shark fin. And it enables us to play with color in a particularly nice manner that is useful for humans and devices. So let's begin. You get this shark fin and you'll see that that represents red. You go along the outer edge and you have all the primary fully saturated colors. You go from red through orange to yellow, through to yellowy green to green, through cyan to blue, down to purple. Interestingly enough, the purple value is an addition of red and blue along this line. So once you hit purple, you go along this line to generate your purples through to red. So you get this enclosed space, which just makes it easier to compute and cope with as a human. So it's also called the equal energy spectrum. Everything's normalized. So that means when you're treating colors here, the red is basically as saturated as the green. They're of equal energy. And that means the center of, or we'll call it the center, or the center of mass of this diagram is white. It's equal amounts of every spectra coming at you and hitting your eye, and that's white. And this diagram enables you to do some nice calculations. So you get all the greens around the surface there that fit with particular values that are matched using experiments. So it's a normalized space. You can take any spectra, any color, and put it into this space. And this space then you can use to compare all the devices. So you might have a print document using cyan, magenta, yellow, and black. And then you might have an RGB monitor using RGB. Your monitor can be calibrated, and then the colors it can generate can be projected into what's called a color gamut. And every piece of hardware has a different color gamut. And the interesting thing is, so here's the print gamut. So that's colors that are printed like this. And the colors that are from an RGB on a monitor, such as you're seeing here when you're viewing this. The overlapping region ends up being the colors that will can be represented on those devices. So this space, so we wonder, why have we gone through all this effort? The reason being, if you say make a game with an image and you want it to appear on devices correctly across a number of devices, you make sure that you choose colors that are represented on as many gamuts as possible. Think about it, you're making a horror game. You use a color palette that's dark. But the problem is you play it on some monitors and people can't see it. This is where it comes in handy. It also means that if you want to show literature in print, which is getting rarer and rarer, but still a thing, still people buy magazines, print posters, they put on the walls, you can make sure your printed colors appear the same. And this is what artists and what people in the industry do to make sure things fit together, because print and emitted color on a screen are different. So these are the color gamuts. The other thing I should mention as well, that's white. That's a fully saturated green. All of the saturated gradients of the color going from the saturated form through pastels to white are along this line. So that means if you want to create a scene that contains a particular shade, say it's a yellow, for whatever reason you want a gradient of yellows to appear in it, you just use that line to calculate it. Very hard to do in RGB because you've got no diagram to really help you. You use this RGB cube. This is a much easier space for humans to cope with because we think of things as colors and as saturation, so how much the color is a full color and not white. So a desaturated color has more white added. A saturated color is its basic primary color. And this is for a normalized brightness. So this slice is at a particular equalized brightness, and the X, Y, and Z are equal to a third. So if we want more bright colors, we can take that slice and zoom it in and out. And so this color space is the basis for a lot of other color spaces as well. So as I said, this is what I've said before. So point of the region edge is the hue. The diagram is a plane. The third dimension is the Y value, just to confuse people, X, Y, Y. The color matching function Y bar is the same as the photometric curve. So that means when you look at, see the Y bar here that generated that shark fin, it matches the photometric curve that I mentioned here. So So they've used that as a sort of a pivot point to create this model. And keep going down here. It's also, this diagram is useful for understanding the limits of various hardware. This matters. You can actually do a Master in Color at Rensselaer Polytechnic Institute in New York, if you want to. And you'll get a job at Canon, you get a job at Kodak, which, yeah, they still exist, they're still making stuff. All the printer manufacturers, Epson, monitor manufacturers, the ones who create the LCD screens that go into your different machines. Do a Master's in Color, you can get a job with them because you working with the researchers to generate colors and generate screens that do consistent color. Color consistency you think is not a problem? Go and have a wander through JB Hi-Fi and look at all the TVs and see how the colors vary. So it is a problem if you're trying to design a screen that represents lots of colors brightly to attract people to buy it. And that's a part of entertainment computing and gaming. So for instance, on the right, I just grabbed this. That's the color gamut for an Apple monitor, the one that I'm recording this video on. So the limits are the limits of the values that can be represented. So the R, the G, and the B guns on the, well, not the guns, the LCD crystals on the display are all only able to generate these sort of colors. Anything outside of that cannot be represented. So that means when you're looking at this diagram, it's not correct. The color fin can never be represented because on a particular device, because there's always a color gamut that it's able to represent. It might get very close, but most of the time, display systems only cover certain gamuts. Lights and other things are fine. They have different physical properties. But a display system like an LCD or an old CRT, if you're still using it, or a projector or a printer will only fit on that space in a limited gamut. So you can't trust the diagram. When you're looking at a CIE diagram on this slide, it's not correct because the color monitor can only actually do these colors. It's just the nature of these diagrams. So you use the maths. You don't trust the color. Okay, so I keep speaking ahead. So the corners represent the most saturated red, green, and blue for that device. Printers and film have slightly curved triangles due to the physical properties of the media. I don't get into that much because we're using digital forms in most of the things we're doing, but it matters if you're trying to represent colors across different media. So it does occur. And you can convert between color spaces. So if you go, in particular on Macs, Windows has color conversion spaces now. The Macs were always the machines that were suited to artists. It's one of the reasons why artists often use Macs, because they have color calibrated monitors. So when you're trying to print, when you're doing lots of printed media years ago, you were using Photoshop and you were printing things out, you could be reasonably sure the colors would match because you had a color calibration space for your Mac, a color calibration space for your printer. Where it overlaps is the set of colors you can use for printed media. So it was a useful thing. So most PCs have this and they're calibrated. And what they do is one method of calibrate. I just use this equation just to illustrate that, say a grayscale conversion based upon old CRT cathode ray tube phosphors, you just have numbers for the weightings. So to make your monitor generate colors that are matchable in the CIE fin, you just have a weighting applied to each RGB. That's what you would see in the system. And you note that, again, lots of green, a little bit of red, and not much blue. Humans don't see much blue. The old encodings for television would send basically a red-green image, and a couple of bits are used to encode blue. because you don't see much blue. It's starting to get out of the range of your vision, just because that's what we've evolved to do. Green is important to us. We encode it far more strongly. So that's why the weights are unequal, because we're sensitive to different colors. And I've mentioned about green being the way we are evolved. We're much more sensitive to green. So the XYZ space, that fin is great. You can improve it. I'm not going to go into it, but should you be interested, just look up the terms CIE LUV and CIE LAB spaces. They're biased to be perceptually uniform. That means as you move across the diagram, a distance, and you go to another part of the diagram and move a distance, you will see those colors as being equally different. So that means you've got far more control over the color again. But what are you used to? So that's the fundamental theory of color, to get it into our space and to compare. You use RGB most of the time. And it's fine because it maps to hardware immediately. Hardware runs on an RGB tri-color system. The problem is that humans don't think that way. Humans use hue and saturation and luminance. So that shark fin works on that model. You've got the fin being the hue. The saturation is from the center to the outer edge, and the depth in Z, so to speak, is the brightness. But anyway, the color cube maps the primary colors on your hardware linearly in 3D. So you know that. You've been playing with these colors. You probably played with these things a lot in computer graphics. You can do that in all the demos that we've shown. It's intuitive in that, well, you understand that you're mixing these colors together, but controlling it for really sensitive and perceptually uniform colors makes it really hard. So that's what you've been playing with so far. Also, you can use HSV and HLS spaces. HSV is probably the most common that you see. And note that it's a disk. So in this case, it's an undeformed shark fin. So imagine if this is the basis you can use. It maps easily just to straight RGB, but the CIE shark fin is a deformed version of that disk. You change the shape by stretching it out to suit the human visual system. So these spaces are what you see again, and in a number of systems, including paint packages and so forth. Hue is represented as a 360-degree angle around the edge. So it goes from 0, which is red, around to red at 360, but it passes through blue just short of that, in through purple. The saturation is the distance between the center and the edge, very similar to the shark fin, but in this case again it's not deformed, so it's just a circle. So pure white is in the center, and all the shades from white to pure red, or a pure color on the edge, follow that line. And then how light it is, its value, goes between 0 and 1. And so at the top here, you have the brightest colors. As you go down the HSV space, it comes down to this cone, which forms the bottom part, which is black. HLS space is slightly different in that it says that all the brightness actually forms a complete cone, and it starts at white, up the lightest color white up at the top, and you don't have any of the primary colors present, and then you come down through here where you have, I guess, the brightest primary colors, so all the saturations go higher up through here, and then you go down to the bottom with the darkest space there. Sometimes it's also represented as a hexagon. Why? Well, probably the points on the hexagon map to the basic colors you think of. So red, orange, yellow, green, cyan, blue, purple. Let's get rid of the orange. So red, yellow, green, cyan, blue. Six points, hexagon. So, right. Then there's printed media. I don't touch this much because it's a different space, not really printing anything, but something that you need to be aware of in computer graphics because you can print out computer graphics. CMYK color model is different in that the basis colors are not red, green, and blue. They are the subtractive color spaces of the complement colors. So it's cyan, magenta, and yellow. So if you mix cyan and magenta, you get blue. If you mix magenta and yellow, you get red. If you mix yellow and cyan, you get green. And because they're subtractive spaces, in principle, you're supposed to be able to add them all together and get a black. But what actually happens is they add K, or black, in order to, they have black as a separate color. And they will use that black to to dull colors back down to a black color. So they have to mix them all together. So it's actually got 4 elements with a separate black because there's no way to make those print values generate a black by adding them together. You get the other shades of color, or sorry, the other hues of color, but you're not able to subtract away effectively to generate a black. And white, it's the color of the paper typically. So this is just the media determines how the color spaces work. So yeah, I've covered this. So the primaries are cyan, magenta, blue, or black. Complementary, they're the complement of red, green, blue, respectively. So C is 1 minus R, M is 1 minus green, Y is 1 minus blue. And that's how you do just a RGB CMY color space conversion very simply. So it's about inks. They're light absorbing and so they don't emit. A monitor emits, print actually absorbs light. So it's an absorption model and it's subtractive in nature. Cool. Yep, so in the end, in the print form, cyan is obtained by subtracting red from white. Magenta is obtained by subtracting green from white. Yellow is obtained by subtracting blue from white. If you want a perceptual version of this, draw a red circle on the screen, stare at it for a long time, and then look at a white wall, and you will see a cyan circle in front of you. The reason being, very simply put, white is all the spectrum, so all your cones and rods are activated at once. You shine a lot of red into them, they get exhausted. So that means that when you look away onto a white surface, the exhausted red cones don't work and you get cyan because you've subtracted red from white. So yeah, difficult to match with monitor color spaces. You need to use that shark fin that I mentioned. It's a problem for people who play with printed media. And it does still become an issue when you're trying to communicate the vision of your game to something that goes on a poster. So it still matters to the games industry, but it's handled by artists more than anybody else. I won't cover it deeply. This is a quick procedure, an algorithm showing how you convert from RGB to HSV space. And in the end, this is the sort of procedure you need in order to make sure that you're able to use those spaces interchangeably inside your applications. So you can convert between these spaces, and get rid of that. And the whole idea is that you use just an algorithm to change the spaces, the colors from RGBs into the hue, the saturation on the edge, and then the luminance height inside the HSV space. So this is just to show that color has issues. Color is a big issue for people who work in the industry, especially if you're dealing with other media. You guys will tend to just make games. But again, as I've said, theory enables you to see more deeply into what's going on, and for you to understand that color is not just RGB. Your perception of color is a very different story using wavelength, and that you need to understand that in order to make color communicate between, to make concepts of color communicable between people, you need a standard space like that shark fin. And in order to do that, you have to do a fair few conversions between spaces. And this is the thing that drives color and the perception of color for humans. So keep this in mind whenever you see color represented to you on different devices or paints or media. Okay, so moving on, we now go to advanced reflectance. So I've talked about color, a bit of the physics behind reflection. So far in this unit, I've taught you some fairly simple real-time lighting and reflectance models. But here we get to start to look at more complex reflectance models that give a better reflectance simulation property. And the reason for this is the world isn't plastic. You need to understand that reflectance, in order to model particular surface properties, you need to be able to make sure that reflectance matches that. So I've talked about, leading up to this, the idea of radiosity, radiance, photometry, leading into color, representations of color for human perception. And now we move to, if we need to make something look like... Okay, so moving on. Sorry, there's a little break there, camera failed. Coming back, so we're looking at trying to mimic things such as metal and other forms of metal, copper, gold, all sorts of things like that. They all have different reflectance properties. This is how you make things look like some material in computer graphics. And this is the basis for those materials you use in Unity. So this is the idea of a material property. And we're extending that past just simple Phong and Gouraud shading into something that starts to mimic more realistically the appearance of objects. So I'm going to look at BDRs. And BRDFs are drawn from empirical measurements using reflectance measuring devices. You do an experiment, you measure the light coming off a surface, whether it's a glassy surface like a phone, ceramics, plastics, they all have different reflectances. And this is what makes us look at it and go, okay, that looks like plastic. We know that. We see that intuitively, but you've got to model it mathematically. So the way to do that, or a way of getting a component of the final appearance, is what's known as a bidirectional reflectance distribution function, otherwise known as a BRDF. I guess if you want to be funny, it's a BRDF. Whatever. And it describes in general how light reflects from a surface. So it's much more general than the stuff I've shown you. It's general. You can show the reflectance properties of some object using the BRDFs. So we've used before Phong lighting. It's very plastic. It's irritating because everything looks like plastic. Now we can use a BRDF to create an arbitrary reflection model, and we can do it by the use of a texture, an environment map more specifically. And so the idea is that we are modeling how light comes in and goes out from a reflection on the surface. That's the simple point. And we do that around the surface normal, remember, with the environment map. So it's an environment map approach, and it can be done cheaply. So remember when I ran that demo in the tutorials, and you could see from the solutions, the checkerboard environment map reflection, it looks like it's made of metal, because metal has that property that it can be, if highly polished, be a perfect surface reflector. So this means that we can generalize from that. We can create other surface properties that start to approximate the way other things look. And so this is what a BRDF is about. So here's some example BRDFs. So if you have just the diffuse value from the lighting equation, it's a simple hemisphere. So the light reflecting off the surface is related to, it's a surface for reflection is equal to the incident light. And it doesn't vary with the viewpoint. So it emits equally in all directions. Okay, so that's the diffuse components that we were calculating in the lighting models. L dot N. Very simply, no I vector, no viewpoint. Here's the Phong light model, or more specifically the Phong-Blin model. Don't worry about the Blin. It's just a sort of slight modification of the Phong model. Note, you have the diffuse component. Remember we calculated diffuse component for that light. And then we use a view vector to determine how close we are to the perfect reflection, and we add a component. So we end up with this lobe that appears. That's the specular lobe. That's the highlight you see. So when I created those balls and made them look like billiard balls, highly polished, plasticky, sort of ceramic-y appearance, that specular spotlight is if your eye is incident with that reflection point. So if the light source is here, it reflects off the surface and goes there. You get a diffuse component, the hemisphere, and then you have this lobe, which is the specular component. So that's the Phong equations that I've been showing you for lighting. But it can get all really different. So there's some reflectance models like Torrance Sparrow. I think this is useful if you want to represent clay and ceramic surfaces. I think it's much more of a dull surface, not particularly specular. But you have a look here. There is a hemisphere. It's a very low hemisphere, a small hemisphere, light coming in, going out. And then there's an offset lobe. The specular component is actually offset from the eye position slightly. Now, that's just been determined, and it gives you a particular appearance. And so this is, the reflection of light around the surface gives you this appearance. Then you can have wards anisotropic. And anisotropic reflection is not equal in all directions. So this specular component is equal in all directions. It just looks like a lobe sticking out. This one here, you have the diffuse component, see it there. The specular component is different in different directions. It's asymmetric or anisotropic. And this is like brushed metal, which you'll see in a minute when I show you the BRDF examples I show you. Now, those two are created as mathematical models based upon generalizations of brushed metal and ceramics. Great. Others can be just determined from looking at measurements off the surface. So for instance, here is the Hapker-Lommel-Seeliger lunar BRDF. The moon has a BRDF. So it's got a diffuse component, this very shallow disk, and then a very odd-looking lobe for the specular component. That's the moon. You can read off the reflectance because you know where the sun is. Just point a meter at the moon and you get this. And then there's the Lommel-Seeliger. There's that guy Seeliger again, with a dusty surface. And so you imagine a dusty surface looks fairly matte. But it's interesting that the dust affects the diffuse component. There's no specular because dust is very rough by definition, sitting on the surface. It scatters light in all directions. And so the response is equal in all directions. It's not anisotropic, but it has no specular component, and it's very flat looking as compared to our standard diffuse model. So this is what we're trying to model. We're trying to model this with a mathematical function. Generally, you get these mathematical functions either by doing lots of experiments and building a model around it, or you just store the BRDF in a texture lookup function. So BRDFs do not model the interaction of light with the materials, just the reflectance. I talk about BSS-RDFs later on. That's about subsurface scattering, so you can model skin. They can be empirically determined from measurements or images. And then analytic versions can be created to fit these known empirical surfaces. And you can approximate this using environment maps. And so I just show you this example because it's a quick way to understand, oh, if we model these things, it really changes the appearance of objects in the scene. If you want that level of realism, you need to use these material properties. So here's an example, a simple example as an introduction. See, we've got a number of objects in our scene, so I'm just going to swap over to an example because it's quite cool. So here it is. Here is a set of objects using BRDFs. Here are the materials down the bottom. And if you look at them, let me check. Yeah, this is bronze. This is gold. This is brushed metal. And this is orange peel. Yeah, that's right. Orange peel has a BRDF. Now, this is not, I mean, probably you'd want to put a normal map on it and make it bumpy, then you'd start to see it make, you're looking like orange peel. But this is just the reflectance. It doesn't include surface sort of undulations or anything. It's just, this is a pill in Unity being rendered as an orange peel. But look at the other one. So gold is quite striking. You can see there that bleeding sort of effect. Oh, that's bronze, gold here. So this is the material, and you can see that you get that sort of, the specular component has that glowing effect that you see in gold. Then there's the anisotropic effect, and this is where it starts to look like brushed metal. So when you come to the poles of the sphere that's used to represent the material here, you see that you get that sort of, that appearance. You've seen that before. If you've got a brushed metal, storage thing, cup, mug, whatever, just stuff that's being brushed metal, you get this appearance. You've seen it before. You also get it when you look at, say, Christmas decorations. They're not brushed metal, but because the cotton is shiny in one dominant direction, you get this appearance. These used to be very popular during the 70s. You don't see them as much on Christmas decorations anymore, but you get a similar effect. It looks like satin. It looks like brushed metal. And so the BRDF is affecting how it appears. And then we've got bronze here, which has its own particular properties. It's still a metal, still has a glowingness about it, but it's got a particular color and a particular sort of glare that occurs on its surface. So this is the results of using these BRDFs. So I'll go back to the theory and I'll probably take you through the demos again. So to do this, we've got to create a BRDF, and it's represented in spherical coordinates, just to throw you, okay? Because what you need to do is you need to represent incoming light and outgoing light. So incoming light has two angles, theta I and phi I. So phi is that angle there, and theta is that angle from the vertical. And then there's an outgoing value, theta O and phi O. Theta is the angular rotation of the vector from the up vector. So you can see it's the angle there from the up vector. Phi is the angular rotation of the vector in plane perpendicular to the up vector. So it's from, say, the z-axis around. Note the radius of this sphere is 1. Just to make things normalized and easy to calculate according to cos theta, sine theta, and so forth. So that means that in general, a BRDF, these things that we were showing here, are actually a function of 4 values. They're a function of the incoming light angles and the outgoing light angle of the two vectors, the light coming in and the light going out. So it models reflectance. And then we add to it just a simple diffuse lighting model. So this is an approximation. It's not perfect, but it's a quick way to get some very stunning effects on your objects in a scene. And so that means the light out, Li is the intensity of the light arriving at the surface, modulated or multiplied by cos theta, I, incoming, and the BRDF function made up of those 4 values. So for multiple light sources, if you wish, your lighting model now comes to your incoming light, the cos theta term for your diffuse, and then the BRDF function multiplying it. for n light sources, all added together and summed, spat out as your outgoing light. So ideally it'd be nice to have a 4D texture. I think you can do it now if you were to write your stuff in CUDA, but for the common purposes of our systems, we have 2D textures. We have 3D textures, but a 4D texture would be a pain in the ass, and I don't think you can really define them. So what we can do though is if you have 4 dimensions, you can split them into 2 sets of 2 dimensions and multiply them together. Sorry, that trick didn't work. To get your 4 dimensions. So 2 dimensions and another 2 dimensions, multiply them together, you get your 4 dimensions. So the common technique is to use 2 cube maps as an approximation for this. And environment maps are an incoming radiance approximation, often used for lighting. So think about it. When I showed you the environment map demo, you're seeing light coming in. Remember I said that radiance is an approximation of, at every point on the surface, a new environment map being generated. So we can use just an approximation using a set of environment maps that use the point on the surface to determine their reflectance at that point using 2 environment maps to tell that information. So that 4D function, the BRDF, can be separated into the product of 2 2D texture functions, G and H. And then they're separated by what's called a Gram-Schmid process so that they can be multiplied together. So that means our BRDF is just a G texture multiplied by an H texture. So its full name is the Gram-Schmid half-angle difference vector parameterization process. And so what we end up doing is that if we use that process, so somewhere, somehow, those BRDFs that I've got in this demo were generated and then split into 2 environment maps. And then we use the latter part of the Gram-Schmid process to blend them together properly so that they will generate for us the correct appearance. So what this is we require an orthogonal projection to create separate G and H functions. Think about it simply. The Euclidean space is 3 vectors defining an orthogonal space. Y, X, and Z. They're linearly separable. So when I specify a value for X, it doesn't influence Y. It doesn't influence Z. They're separate. And so a point in space is 3 values, X, Y, and Z. It's not X and a little bit of X, Y, and Z. It's not Y and a little bit of X and Z. And it's not Z and a little bit of X and Y. You specify them separately. They're linearly separate and orthogonal to each other. Put simply, the Gram-Schmid process enables the generation of vectors to sample that space effectively. So what happens is that these values are generated inside the shader to give us the correct vectors as a basis for the sampling of the environment map. So it's a bit more complex than the standard environment map shader. Once that's done, if we want to generate the cube maps, what happens is for each face of the cube map and each texel of the face, you compute a vector from the origin through the texel center, and you compute the spherical coordinates of that vector, and then you look up the RGB function values for the G or H function and write those into the texel. So this is how you generate your cube maps. And then you spread the values around if you're using linear interpolation to generate texture sampling, just like the texture sampling I showed you in the last lecture. So that's been done offline for you. This is the general process. And then when you want to use the BRDF, before that, it generates these textures, and here they are. These are two environment maps, and put simply, now this is just putting simply because it's split the two functions. There's 4 dimensions, it's to split them based upon phi in and out, theta in and out, to generate G and H. You can see here it sort of approximates something like this is the specular component and this is the diffuse component, but I'm being very simplistic there. But as you can see, even looking at the maps, you understand why you get that glow that occurs, because the maps look like a glowing surface surrounding it. And we're sampling it and making the object look like gold by doing that. So then to use those previous setups, you just set up 2 textures as environment maps, H and G, and set them up on your texture units. I'll just say it's texture 0 and texture 1. Let's not call it a unit. I copied this from a paper. Let's modify it. And for each vertex, compute the texture coordinates used to index the G texture. So it's an environment map sampling. And for each vertex, compute the texture coordinates to index the H texture, which is another environment map. Then calculate a diffuse color component. So this is just standard Phong diffuse color. And then once you've done that and you sample the textures, multiply them together, and then multiply that by the fragment color. So maybe you've made it a red steel or a blue steel or a green steel, up to you, for you, say, the anisotropic. And lo and behold, you will end up with what we see in the demo. So in Unity, because I got this from some code, for whatever dumb reason, NVIDIA decided to change their implementation to G and D. So H is now D. So you have 2 BRDF textures to use. It uses a Gram-Schmidt process to determine the cube map coordinates to match the previous processing to make an orthogonal. And then you just sample from the environment maps, blend them together, and get the final appearance of the object. So you can see it here. So on the vertex shader, we just have the projected points coming in and going out. That's all fine. We calculate the world position for the objects. That's all very good. And then the world position is used with the light position to generate the angle to the light. And then we normalize that. So this is simply the Gram-Schmidt process. There's a couple of lines there. And then we calculate a half angle vector between the eye and the light for our components. And then, sorry, the Gram-Schmidt process is here. The red part is where we generate our coordinates for the H texture and the D texture, and this is where the Gram-Schmidt process is applied. And finally, we generate a world normal and also a diffuse value for that vertex. So that's just the standard lighting model spat out. Once that's done, the pixel shader becomes trivial. It's just you either do, you just simply sample the texture for the H value and the D value. That should be, why did I call it color D? That was really, I need to go back and look at that code. But anyway, they're the 2 textures. You multiply them together and then maybe multiply them by another value just to make them brighter. And lo and behold, you end up with what we see in the examples that you see here. So the only tricky bit is this Gram-Schmidt process. But put simply, as you can see with the textures that are set up, so this is the gold diffuse, and then there's the gold specular. That's G. Where's the H? There's the H value. As you can see it reflected on the sphere, creating that effect there. It becomes quite, it just suddenly changes the appearance. They don't look like plastic. they look like metal. That looks like a metal. Looks like a shiny metal. That looks like a brushed metal. And this BRDF function therefore enables you to generate these quite realistic looking appearances. Now, as I often hear, why are we doing this? Because that's what Unity uses. That's how they generate things that look like cloth, that look like maybe a plastic mask. This was a demo that came out with Unity 5, but it still applies. They use BRDFs in their physical lighting functions internally in order to give you an approximation of various materials, the metallic materials, plastic materials, and so forth. So you don't really access that. I've shown you a simple method for doing it. They will have their own internal functions delivering BRDFs for the colors on their surfaces in their shaders. So if you want to, again, crack open a wine and have a look inside the shaders, and if you want to really get deeply into that. But just understand, to get a particular material, surface, appearance, a BRDF for reflectance at least is required. And you just need to understand what a BRDF is. I've given you a simple demo of what it can do to change the appearance of objects. They will have their own implementations, and that will enable you to understand what they're talking about. And they're talking about a bidirectional reflectance distribution function. Now, a final part is that in order for this bidirectional reflectance distribution function to work, it needs a tangent coordinate system on the surface. Now, I get into this more detailed manner in normal mapping lecture. So suffice to say that you know what a normal is. It's the vertex normal or the surface normal, depending upon how it's being calculated. And then, in addition, often the models that you get will compute a tangent. So Unity gives you the ability to actually compute tangents. See here, normals and tangents. Calculate a normal from the mesh. Calculate tangents. So the normal has the normal semantic. The tangent is another semantic called tangent, normal. There it is there. So that comes through in your mesh once it's been calculated over here. But note, the binormal that is used in some of these calculations, you need to create yourself. And remember, I covered last week in the tutorial the cross product. The cross product of the normal and the tangent gives you the binormal. And the binormal is what we're going to use inside our environments. I'm going to take you through this again a few times just to get you to understand these spaces that sit on top of objects. It's going to be a bit of a leap for you, but these are used so much, and you actually have to be able to understand why it is you create these tangents on the surfaces in order to generate correct normal maps and perspective occlusion maps and so forth. You need to understand these spaces. But they're just the same as the Euclidean space. The normal, the binormal, and the tangent. They're all at right angles to each other, but they sit on the surface of an object at the vertex. In addition, some bits and pieces, just covering the pipeline in Unity for Direct 3D. Remember, I've been referring back to this. We've covered all of this up to this point. I think I covered clipping space last week and just covered clipping. Then there's the viewport transform. Viewport transform is what converts from the clipping space into the final screen space at the pixel level. And the reason why we go through this is because you have to get your image. So you've done all your calculations over here, you created your model, they're animated, they're doing stuff. We've got to see it. We've got to see it on a two-dimensional screen. We don't have holographic displays. If we had holographic displays, where we just look and see things, you don't need anything past a camera model. So you just need to clip. Once you've clipped, You just blast the voxels into the 3D space. But we now need to do something else. In fact, you wouldn't project. You don't need to project. You just look. You have a 3D space in front of you, and it's where things are generated natively. The problem is we're doing things in 2D, so therefore we've got to change and convert these clipping spaces into a viewport. So there's a viewport transform and then a divide by W to generate your screen space values that are needed. So a viewport is just a rectangular area in device coordinates or normalized device coordinate space. Okay, it's the thing that sits on, it's talking about the window you're rendering into. You're starting to talk about getting pixels spat out. And this indicates where on the device, you know, the full Mac or Windows machine you're using, it starts to get down to the point of I'm just going to start generating pixels and fill the frame buffer with pixels in the triangles. So by default, that's the entire screen. And old graphic systems used to be like that. You didn't have a windowing system. I remember using years ago some old Hewlett-Packards. And you would program it in Monitor Basic and it would just generate the graphics. For those of you who are old enough, you might remember using Apple IIs. Apple IIs were like that. There was no viewport transform because the screen existed as a screen and you just referenced the raster scans in order to generate your images. You're used to windowed systems. Because it's a window, the GPU's got to know where to blast out the fragments. That's the viewport. Okay, and the viewport then, so your window that you're rendering in then gets transformed into a pixel space. The camera failed again, so I'm back with a bit of a jump. So again, it's getting my thread back of consciousness. Your window you're generating your graphics in is then going to be placed somewhere on your device. And that's a viewport transform because your GPU is rendering to hardware memory. And so it's now starting to say, tell me which pixels to draw. Because it could be that, you know, when you grab a window and move it around, it's just, no, that's not, maybe that's a good way to do it. See, I'm changing the viewport on the display. So the graphic system for Unity that's rendering into this scene using, on my Mac, OpenGL or Direct3D on your Windows machines, it's got to change where that window is. So the GPU's got to know, so the graphics library needs to tell it, and that's done by the viewport transform. As you can see, this window we're rendering in, I've switched it over to the left-hand side here, and it's moved on the screen. So the GPU's got to know where to put its pixels. And that's what the viewport transform is. And you don't perform the transform. It's effectively a scale and translate of your window to suit a particular space on the device. And then the rasterization begins to generate the pixels that will be placed into the screen. Okay? But you specify it using a viewport rectangle. Okay, so you're telling Unity that this is the size of where I am, and then the graphics library says, oh, by the way, your window's over here, and then the GPU then knows to render into that viewport over here. If you didn't have a viewport transform to cope with these sort of different viewports, it would just fill the entire screen with the graphics. It's fine. A lot of games work that way, so you don't need the viewport transform. It's just set to Unity, pun intended. But the idea then is that no, a lot of games and things run in Windows, graphics systems run in Windows, you need a viewport transform. And that's covered by Unity. But there is that scale and translate to create the viewport in the device is handled by your graphics library. And drawing from the Direct3D code, you've got a window a normalized window space that is not rasterized. It's just the window is at some scale and dimensions and so forth. But then you specify that the viewport is some number of pixels on the screen. And that's the viewport transform. And so what happens is there's a mapping from the viewport, so from that window to the viewport. And what you see is that if you looked at the matrix, not the matrix, which controls reality, but this matrix here, you'll see that it's just a scale and a translate. That's all it is. So this window in abstract window space then gets mapped to a physical viewport of pixels on the screen. And in the end, that final viewport depends on what the windowing system does. So if the windowing system, so when you grab the corner of the window and scale it, you are changing the viewport transform. The GPU then knows, oh, I've got to generate this many pixels, so it just keeps up with that viewport transform. So that's all that is about. So you control everything up to the clipping space, which is done in this space. Things are clipped, you've got a window in a normalized space, and it's mapped to the device coordinates, which generates a window in pixels on the screen somewhere on its space. And that's all a viewport transform is. You control it by setting, the size and width and locations and so forth, and then away it goes. So if you want to, in your game, you can set the viewport and you can have multiple windows distributed around the scene. Some of you may have played with that. Some of you may have played with generating viewports and generating maps in different locations. Though most of the time that's done using a quad and just blitting a rendered texture onto it. But you can do it with viewports if you wish. So that brings us to the end of the lecture. So this is about different reflectance models. So we can make things not look like plastic and make them look like real materials. Thank you for listening. See you in the tutorials.